Boom. Hello and welcome back to Calculus 1, Part 2 of this lecture 4.5. We have to deal with the differentials. Let's quickly review the linearization part. Quickly means why and how in a few sentences and maybe one example, and then go on. So the idea of linearization was to compute the tangent line close to the point of interest and then compute the difficult value in the tangent line, which is a simple calculation, rather than computing the point of interest in the difficult function. So idea was to just use the formula. You see it's a tangent line because you have that f of a, that's the y value for the given function. You have the derivative computed at a, that's the slope. And then we have x minus a. This is just one of those. This is the form, you've seen this form before in algebra. It's the y minus y1 equals m times x minus x1. That's the form. Except that y minus y1, the y1 is shipped to the other side, and that's your f of a. So it is, let's see another example from the book. So say question is to compute the value. Again, remember, right, what we are dealing here with. Desert island, no calculator, no cell phone. Wilson is gone. You have nothing else to do. You're building this shelter, and then you need to figure out, let's say, sine of 0.75. Now, this is, when I say 0.75, that's clearly radians, right? Because I didn't put the little degrees. Sine of 0.75 degrees, we can just call that 0, right? Because that's less than 1 degree, right? But because it's 0.75 without a little sign for degree, then this is 0.75 radians. Now 0.75 radians, that's less than 1 radian, and then you have 2 radians, and you have 3 radians, and then you finally have 3.14 radians, which is pi radians, which is half a circle, right? So 0.75 radians, if you draw your unit circle, you know that over here is pi radians, so therefore over here is 3 radians. That means that somewhere over here, or not over, is 2 radians. Over here somewhere is 1 radian. So therefore the value that we want is somewhere over here, 0.75 radians. So that's the idea. That's the angle theta that we want to compute. Now, looking at this picture, there I say it should be clear that the easy value for us to compute is at pi over 4, because that red line is very close to the quarter of the, right, the pi, or, 1/8 of the full circle, and that's at pi over 4. So I am going to draw this and say pi over 4. So it seems that I just say looks like the easy to compute value is pi over 4. This depends on how, precisely you draw these things. It could be pi over 6, which is 30 degrees. It could be pi over 3, which is 60 degrees. We can just, say, all right, let's use pi over 4. So now I have my linearization equation. Now, what is this pi over 4? This pi over 4 is that A is pi over 4, right? So my linearization function, L of x, is going to be f of pi over 4 plus the derivative at pi over 4 times x minus pi over 4. So this is my linearization equation, and now we just compute the whole thing. So L of x is going to be function at pi over 4, well, that's sine of pi over 4, we can get that, plus the derivative of sine is cosine, so now I need the cosine of pi over 4, and then x minus pi over 4. So these are the things that we can calculate easily, right? L of x is root 2 over 2 plus root 2 over 2 times x minus pi over 4. Now you can use the basic calculator, right? You can use the basic calculator to come up with numbers for, like if you want the decimals. Now, this is nothing that you can't do in a sand with a stick and with the ample time. But just in the interest of time, I'm going to use calculator to plow quickly through this. But you can go and you can get your square root of 2 value rounded, right? So you would round that one to 141. You divide that by 2, and then pi round to 3.14. Divide that by 4, right? Long division in the sand. Everything here can be done on a paper without a calculator. That's the purpose of the whole thing. So let me just get you some of these decimals. So we are looking at 0.707 plus 0.707 x minus, and pi divided by 4 is 0.785, since we are going 3 decimals everywhere. And now combine all of the terms. So L of x is equal to, what do we have? 0.707x when we distribute. And then we have 0.707 times 0.785. That's going to be negative, and then minus 707. So it's going to be plus 0.152. So this equation is actually the tangent line at pi over 4 for sine function. And now this is what we claim. This is why we do linearization. We say sine of 0.75 is going to be approximately the same as L computed at 0.75. So we have 0.707 times 0.75 plus 0.152, and now you just compute this and you're done. So 0.682. So that's what we are getting. Now I am going to go sine of 0.75. So calculator on sine 0.75 says 0.6816. But if we round, well, I'll put all decimals, 3876, this is what calculator gives. Now observe that if you are to round on the third decimal, right, that 6 would make it into a 2, and that would look the same. Now, as I said, all of the work that we did, you should be able to calculate these things. Yes, you take time, it's effort and it's sweat, but you should be able to compute the same value on the paper. And you see that it's extremely, extremely close. So, linearization will help you approximate function value. I'll write that in blood over here. Linearization approximates value of the function. And it's important to understand that because now we are switching gears, we are talking about the differential, and differential is going to approximate the change in value of a function. So it's going to be a little bit different. So now we're talking about differentials. Differential. So I will start with the purpose sentence, which is the red stuff. So differentials approximate the change in function, let's say output or output value. Output value. So linearization approximates the output value. Differentials approximate the change in output value. So there's a difference between them. They both can be used to compute the same stuff. So I can also use differentials to compute ln3, but it's a different process because differential calculates different things. So we can calculate same stuff in a different way. So let's see what this whole thing is. So we start by first creating differential formula. And it's a very simple manipulation on your pre-calculus formula y equals f of x. When you write y equals f of x and you differentiate both sides, on one side you use Leibniz notation dy dx, on the other side you use modified Newton's notation with f prime. This is just writing things down. We haven't actually done anything special. And now what we are going to do is this move dx to the right. So now we're going to have dy equals f prime of x dx. This formula over here is known as the differential. This dy is called the differential. Now, what does this mean? Meaning, well, first of all, we have a concept of change. And concept of change is captured with this delta. So when you say delta y, you mean y2 minus y1. When you say delta x, you mean x2 minus x1. So delta x and delta y are both exact change in value. And it's very easy to compute. It's just subtraction of two numbers, right? Now, the change in x is the same as dx. And here is the line that defines our differential. Change in y is approximated by dy. And this is where the approximation comes in. So now you would say, well, wait, isn't it easier for me to compute the exact change? And I say, yeah, because you have calculators and computers. I already told you that the entire section today is something that we rarely use. We actually use it to build up more powerful mathematical structures, some of which you will see in Calc 2, to deal with much scarier mathematical situations that are needed in physics and engineering. This section on the level that it's taught in Calc 1 is completely useless, like 100% useless to anyone and anything with today's calculating capabilities, right? You all have computers in your pocket that are insanely powerful. So none of this stuff in the lecture is actually needed, other than the aspect that it can be upgraded to some things that computers cannot do yet. I mean, yet. And then let's end it there. So, what is the idea here? I'm going to give you a very... I gotta call this stupid example, because it is a stupid example, okay? Let's say you have f of x equals x squared, and your input x value grows from 2 to 3. So if you want to calculate delta x, that's simply 3 minus 2, and it's 1, so change in x is 1 because the value went from 2 to 3. Now let's see what happens with the f of x. Well, f of x is now f of 2 is going to be 4, and f of 3 is 9. So we see that the y value actually grows from 4 to 9. So delta y is 9 minus 4, which is 5. What you see here is the exact change. It would be absurd for me to use differentials or anything else to compute this type of a change, because it's just square two numbers and subtract them, right? This procedure is supposed to work on scarier stuff where computing this is not pleasant. Like a change of a square root of 4 to 4.3. Good luck computing, right? Square root of 4.3, which would be one of these two guys, right? You would have to invoke the previous linearization to do that. Now, so what do differentials do? Differentials say, instead of computing the exact change delta y, I can compute easily, I can compute dy, which is close enough. Because generally you don't need things to be precise to 15th decimal when you are dealing with, you know, almost everything that we deal with as a species. Clearly, if you're a particle physicist, you are going to worry about these kind of things. But if you're an engineer, you're not, right? So let's go and take a look at the differential issue. I mean, procedure, not issue. So say that you want to compute the change in f of x square root of x when x goes from 4 to 4.3. So you are not computing square root of 4. You are not computing square root of 4.3. you don't care about those y values at all. What you care is the difference of those two y values. Because it's like, you know, cause and effect. Right? A little change in the input causes some change in the output. And you only want to know what's the change in the output. You don't care about the values, you don't care about, right? So now, what do we do to calculate this? Well, simply formula says that your exact dy, which you kind of don't want to compute because you have to take a square root of 4.3, is approximated by the change of dy. And the change of dy is a joke to compute because it's just derivative of f of x times delta x. Now both of these are joke to compute. You know how to find the derivative. The derivative of square root is 1 over 2 root x. And you also have that your x is equal to 4. So computing that is a joke. And then you have your delta x to be 4.3 minus 4, which is 0.3. The whole thing is nothing. So delta x is approximated by dy, and dy is equal to 1 over 2 square root of 4 times 0.3. This is 1 over 4 times, I'll put 3 over 10 because I can, and it's just 3 over 40. So, oh, why I put delta x? It's delta y over here. Sorry. So change in y is approximately 3 over 40. That's what it is. So I'm approximating the change. With the differentials, I'm approximating the change. And that's that. Problem done. Now, what can I do with this change? I can actually use this change to compute 4.3. Because wouldn't you agree that the square root of 4.3 would be actually square root of 4 plus 3 over 40? Right? Because if you observe this 4.3 has a base of 4. And then a little bit more. So, wouldn't the square root of 4.3 be square root of 4, which gives you the most of a number, and then just a little bit extra. And that's the change that you get in y. So you can compute, you can use this differentials to actually compute everything that we computed with linearization. Because you can compute the base number and then just fix it a little bit, right? With the differential, and that's that. But you can use it for much more. A lot of word problems would be interested in calculating differential rather than calculating the exact value. Now, I actually want to calculate exact to check and see if this is, you know, any good. So, I think I do it in green in general. Check. I'm just going to go and say f of 4.3 minus f of 4, right, which is the square root of 4.3 minus square root of 4. And I better get a number that it's very close to 3 over 40. So let's see, square root of 4.3 minus 2. Square root of 4, I can do that. So calculator gives me 0.073644, whatever, plus more decimals. And 3 divided by 40 is 0.75. 0.075. We are 1/10 of a centile off, right? So linearization, i.e. the tangent line, approximates the function value, and differentials approximate the change in function value. That's the difference between the two, and now both could be used to calculate values of numbers and things like that, and I outlined over here. So let's see Use differential to compute, and let's pick something that we did with linearization. ln3. So ln3, we did this with the tangent line approach, and we got 1.111111, right? So that was calculated by differential. So let's go do ln3 using differential. To compute. Actually, I don't want to like compute, to approximate. ln3. All right. Well, what is the conceptual idea behind all of this? Find a value that it's close, that it's easy to compute, and that better be e, right? So we're going to use a equals e value. Well, let's just say x equals e. Yeah. So x equals e is something that is easy to compute. So now what do I want? I want to say that ln of 3 is going to be approximated by ln of e plus dy. So that's technically what we are doing here. E is smaller than 3, so ln of 3 is going to be bigger than ln of e. So ln of 3 should be approximated by ln of e plus whatever the change in y is, and that's where the differential kicks in. The specs are, we are using x equals e and f of x equals ln x as a function. So now all I need to do is to compute dy. So ln 3 is going to be ln e plus, and dy, we know from the formula, is the derivative, which is 1 over x, times delta x. And now I just need to compute these values. So first of all, I know x is e, so I can plug that in. ln 3 is ln e plus 1 over e. And delta x is just the difference between 3 and e, so 3 minus e, right? That's the difference in x values. The one x value you want is 3, the other one that it's easy to compute is e, so the difference in delta x is the difference of the two, so I can just put over here 3 minus e. All I need to do is to compute this. So ln 3 is approximated by, now ln e is 1. I know I've been copying it forever, but here we are computing. So ln e is 1 plus 3 over e minus e over e. When you distribute 1 over e to both. And I hope you guys see that positive 1 and negative 1 will cancel. So all you get is 3 over e. You actually had 3 over e over here when you did linearization for this. See? It's 3 over e. It was done a different way, but you got the same answer. ln 3 approximated to 3 over e. We got the same thing. So we still get about 1.111111. We do the same calculation. Again, stick in a sand. No calculators necessary. Approximately 1.111 going on forever. So we can use linearization, or we can use differentials to compute function values. Now what I want to take a look is at least one of these word problems that we have. They have like 3 or 4, 5, 6, no, 6 problems in the book, if I counted this correctly, I mean. Let's take a look at whatever they have here. Approximate the change in volume of the right circular cone of the height. Okay, so problem 38. Approximate the change of volume. So dV is approximated by delta V is approximated by dV, and that's what they're after. Of the right circular cone, I'll draw a little cone right there. The fixed height of 4, so age is equal 4 forever, where the radius goes from 3 meters to 3.05 meters, and that's that. And then this pathetic book gives you the formula for the cone. Really? At this point, you know this is a spiky object, so it's 1/3. Area of the base times the height. Base is a circle, pi r squared, so there should be no issues to know the area for this thing. Now, the very important part to zoom on here is the part that fixed height. That is extremely important, because if the height changes and radius changes, you have a two-dimensional input that changes. That's a Calculus 3 problem. You are going to do this problem 38 in Calculus 3 again from scratch, and you will have to use partial derivatives and the total differential formula that it's presented in that lecture, because the height will be changing and the radius will be changing. Now, we create a Calc1 problem by simply fixing either radius or the height, and then we don't have to worry about total differential. So the only variable that is changing here is r. So now when we take the derivative, we are taking the derivative in respect to r, and we can just plug h in. So you know what I'm going to do? I'm going to say that the volume formula for this particular case is going to be 4 pi over 3 r squared. Please don't confuse this with the volume of the sphere, because sphere is r cubed. One of the dimensions in our case is age, and that was hard-coded to be 4. So that's the reason why we have this. All right, so what is my dV equal to? dV is going to be equal to the derivative of a v, so that's dV dr, times delta r. If I want to use the new notation, it's still derivative times the change in the independent variable. It's just that we are using the new values. dV dr, so now I have 8 pi over 3r times delta r. So that's the derivative. Delta r, that should be clear that it's 0.05, because you are subtracting new state minus the old state. And the r is 3, right? Because that's where the system starts evolving. So change in v is change in v is equal to, well, actually let me go. Delta v is approximated by dv, which is equal to, and now I have 8 pi over 3 times r is 3 times 0.05. 3's are cancelled. 8 times 5 is 40, 0.4 pi. So change in volume is about 0.4. It's about 1.2, right? It's like 4 times 3 is 12. So about 1.2. So what do I have? 0.4 times pi, let's see. 1.25, 1.26. So, okay. So, change in volume is approximated by dV, and dV is about 1.25 or 26. That's good. And that's the answer to the question. Now, you can go and you can compute the exact value if you take your volume formula, plug 305, and plug the other thing. So, let's see what's the exact value, just for fun. So 4 pi over 3 times, open parenthesis, 3.05 squared minus 9. So if I am to calculate exact, just to check, delta V is approximately given by 1.267109. So those are the decimals that calculator gives me if I actually use the formula and plug in 305 squared and then compute everything and then plug the 3, compute everything and subtract it. So the actual change is this number, and the one we computed with the differential is this number. Same. That's that. So that's the section on linearization. What we do is we utilize derivative to approximate function values and change in function values. And it was very important to have this technique before the era of calculators and computers, because there was no other way to compute ln of 3 and sine of 7 and stuff like that. So, as I mentioned before, just 50 years ago, engineers used to walk around with a book called log tables, and then you flip through the book. Actually, some of my students in the past found that very interesting concept, and they looked up these books on eBay and stuff like that, and buy them for $5-10 just to have them as a relic. Because how often and then someone tells you on the exam when you move to the 4-year school, no calculator in the exam. There's a loophole. I got a book. It's not a calculator, right? I can look up cosine and sine and ln and square root of any number I want, because now I have a book of values, right? Now, these methods were used, guys, to compute all of those, particularly, in 1800s and so on. As I said, captains of the ships, right? They have nothing to do. Execution and food and sleep and all right, that's that. Let's reset for the next.